Welcome to the Deep Dive. We're the podcast where we take a stack of sources and really get into them, pulling out the key insights for you.
That's right.
And today we're looking at something maybe a bit unexpected. We're connecting these really old philosophical ideas, some centuries old,
Yeah, ancient stuff.
to the AI systems you're probably using right now. How can thinkers like Locke and Hume possibly be shaping modern machine learning?
It sounds counterintuitive, doesn't it? But it's a deep connection. And that's our mission for this deep dive, to really uncover those philosophical roots, specifically focusing on empiricism.
Empiricism, okay.
Yeah. We'll unpack how figures like Locke and Hume kind of laid the conceptual groundwork. We'll look at the successes, the triumphs of this approach in AI,
Sure.
but also, critically, where the limitations are. We're drawing on work from Yelvin and Yelvin, Vadinsky, Kinch, McClure, Carruth, a whole range of perspectives.
Got it. So the goal is to get a clearer picture of what makes AI tick and maybe where it falls short.
Exactly. What makes it seem smart, and what are the big hurdles still ahead?
All right, let's dig in then. So the philosophical foundation, got to start with John Locke, right? And his idea of the mind as a blank slate.
Tabula rasa, yeah. It's this radical idea, especially for his time, that we're born essentially empty of knowledge. Everything we learn comes through our senses, through experience. No innate ideas.
And that connects to AI how? Because, algorithms aren't born.
Well, no, but the design mimics it.
Mhm.
Empiricist AI algorithms are often built to start with very little pre-programmed knowledge. They're initialized, often randomly.
Randomly, like just guessing at first.
Pretty much, yeah.
Yeah.
Vadinsky talks about this randomized initialization is key for neural networks. It lets them embody that blank slate idea. They then learn, generating outputs based purely on the input data they process.
So they really are learning just from experience, like Locke suggested for humans?
In principle, yes. But, and this is a big but right from the start, it raises a critical question, one you might be thinking about already.
Right.
Well, if a system starts with too little structure, or maybe not enough data initially, can it actually learn effectively? Can it generalize beyond what it's seen?
Ah, right. Can it figure out rules that apply to new situations?
Exactly. And this points towards something called inductive bias. The idea that maybe, just maybe, you need some kind of built-in assumption or structure to kickstart learning properly. A completely blank slate might be too blank.
Okay, so it's a fundamental tension. Start empty or give it a little nudge.
Precisely. And this core empiricist idea, learning from observation, really defines the main ways AI learns today. We generally talk about supervised and unsupervised learning.
Right, supervised learning. I feel like I hear that term a lot. What's the essence of it?
So with supervised learning, the algorithm gets a training data set where the answers are provided. Think input-output pairs.
Like flashcards. This picture is a cat, this sound is hello.
Exactly like that. It gets annotated examples. And the algorithm's job is to adjust its internal workings, its parameters over and over again, trying to match those inputs to the correct outputs.
Through trial and error.
Lots of trial and error, yes, with feedback each time. It gradually gets better at approximating whatever pattern is in the data. And it's incredibly effective for certain things.
Like image recognition.
Perfect example, image recognition, speech recognition. Tasks where you can provide lots of labeled examples. It's been a powerhouse.
Okay, so that's supervised learning with the answers provided. What about unsupervised? That sounds harder.
It is, in many ways. Unsupervised algorithms get only the input data. No labels, no answers.
So what's it supposed to do?
Its job is to find the structure within that data, to discover patterns, often by grouping similar inputs together into clusters.
Ah, like finding natural categories in the data itself.
Precisely. Vadinsky mentions clustering algorithms, trying to find these meaningful, non-overlapping groups without being told what the group should be. Sometimes this involves techniques like dimensionality reduction, too.
Dimensionality reduction. Sounds complex.
It just means taking really complex data with loads of features, and simplifying it, boiling it down to its essential components, making it easier to find patterns.
Okay. But does unsupervised learning always find meaningful patterns? Patterns that make sense to us?
Ah, well, that's a key criticism. Sometimes the clusters it finds,
Mm-hmm.
they don't really correspond to sensible categories, semantically meaningful ones. It might group things in ways that seem random or unhelpful to a human.
Which brings us back to that inductive bias idea, maybe. Does it need more guidance?
It certainly fuels that debate.
Yeah.
Is just finding statistical patterns enough for real understanding? Or do you need something more? It's a really central question in AI.
It definitely sounds like it. And that brings us, maybe surprisingly, to another philosopher, David Hume.
Right, Hume. Building on Locke, but with his own distinctions.
He talked about impressions and ideas, right? What was the difference?
Impressions are the raw, vivid sensory inputs. What you're seeing, hearing, feeling right now. Ideas are fainter copies, memories, or things you construct in your imagination, derived from those initial impressions.
Okay, raw data versus processed thoughts. Sort of. How does that relate to AI?
It maps incredibly well onto a core AI process called feature extraction, especially in areas like computer vision.
Feature extraction, so pulling out the important bits.
Exactly. You start with raw sensory data, maybe millions of pixels in an image or complex audio waveform. That's like Hume's impression.
Okay.
Feature extraction then transforms this raw data into more useful representations, the features. These capture the important regularities, edges, textures, shapes in an image, for example, while hopefully discarding irrelevant noise.
So it's simplifying the input.
Yes, simplifying and structuring it. Carruth and others argue these features are like Hume's ideas, derived from the raw data, processed and made ready for the AI's brain, the machine learning algorithm, to work with.
Even neural networks do this. I thought they just took in raw data.
They do, but they actually learn to perform feature extraction internally, often in layers. They build hierarchical representations, from simple features like lines to more complex ones like shapes or objects. It helps them make better predictions.
But extracting features, doesn't that involve making choices? Deciding what's important?
Absolutely, that's a challenge. The design choices can be subjective, and there's always the risk of information loss.
You might throw away something important by accident.
Potentially, yes. How do you make sure you extract the truly salient features without discarding subtle details that might be crucial for more complex reasoning down the line? It's a big balancing act.
A fundamental challenge. Okay, so we have these empiricist foundations, these processes like feature extraction. How well does it all actually work in practice? What are the big wins?
Oh, the wins have been significant, really transformative in some areas. Think about speech recognition on your phone.
Yeah, it's gotten pretty good.
Incredibly good. Kinch and others reported neural networks achieving word error rates down in the 8–14% range, even in noisy places. Often these systems use things like hidden Markov models, HMMs.
HMMs. What are those, quickly?
Basically, they're probabilistic models.
Mm-hmm.
They look at sequences like words in a sentence and predict the next item based on the probability of it following the previous ones. Think of it like a sophisticated guessing game based on patterns it's learned.
Okay, so pattern matching on sequences. And what about games? I feel like that's where AI really made headlines.
Yeah. AlphaGo from Google DeepMind is probably the poster child here, beating the world champion in Go. That was huge.
And that was based on these empiricist ideas.
Fundamentally, yes.
Yeah.
It used deep reinforcement learning. That's a mix of reinforcement learning where the system learns by trial and error, trying to maximize a reward signal.
Like points in a game.
Exactly. Maximize reward through interacting with the environment, the game board in this case. And it combines that with deep neural networks, which are great at learning complex patterns from huge amounts of data.
So AlphaGo wasn't programmed with Go strategies. It learned them.
It learned by playing itself, essentially millions and millions of games, processing vast numbers of board positions. It showed that this scaled-up, data-driven, empirical approach could achieve superhuman performance in a really complex domain.
Wow. Okay, so the successes are undeniable. But you mentioned limitations earlier. Where does this approach start to run into trouble?
Well, a really critical risk, especially with supervised learning, is something called overfitting.
Overfitting, I've heard that term. It means it learns the training data too well.
Precisely. It performs brilliantly on the specific data it was trained on, but it fails, sometimes badly, when it encounters new situations, novel data, or things that are a bit ambiguous.
So it memorized the test, but didn't learn the underlying concept.
That's a great analogy. It becomes too optimized for the training set and can't generalize, which really highlights something crucial.
What's that?
The importance of the data itself. You need really well-curated, diverse data sets to build AI systems that are robust and can actually handle the real world. Garbage in, garbage out, amplified.
Makes sense. Are there deeper critiques, though, beyond just overfitting?
Oh, yes. There are more philosophical challenges to the whole underlying idea, the information processing assumption.
Which is the assumption that intelligence is just manipulating data.
Basically, yeah.
Yeah.
That it emerges from mechanically applying rules to data-driven features. But critics like McClure argue this is just inadequate. It doesn't capture vital parts of human intelligence.
Like what?
Things like our background understanding, common sense, context, our intentions. the stuff that really guides our thinking beyond just processing sensory input.
So the why behind the what.
Kind of. And Hubert Dreyfus, another major critic, argued that this kind of AI struggles with intuitive behavior. Humans have these layers of implicit knowledge we draw on unconsciously. AI lacks that.
So it feels brittle. It works in its narrow domain, but breaks easily outside it.
Often, yes. Dreyfus said genuine intelligence requires intuiting your surroundings and reacting fluidly, not just applying learned rules rigidly.
And there was another problem, the grounding problem.
Right, Vadinsky brings this up. The symbols or features inside the AI can represent things statistically, but the system itself doesn't understand the meaning. It doesn't grasp the connection between its inputs and outputs in a way that we would call comprehension.
It knows that X often leads to Y, but not what X and Y actually are in the world.
Exactly. It's pattern matching without genuine understanding. And all these critiques together, they really suggest that pure empiricism, learning only from data, might not be enough.
So we need something more to supplement it.
That seems to be the consensus among critics. We might need to build in principles related to causality, common sense reasoning, context, things that allow AI to go beyond just statistical correlation and start to, well, understand.
Okay, so wrapping this up, it's actually quite amazing how these old philosophical ideas from Locke and Hume about blank slates and sensory impressions
Yeah, hundreds of years old.
are so deeply embedded in how we're building AI today. The core concepts are right there in machine learning.
It's a direct lineage, really.
Mm.
And understanding that history, including the limitations pointed out by empiricism's critics, it's not just academic.
How so?
Because understanding the limits of just learning from data tells us where we need to go next. It guides efforts to improve AI, to make it more robust, more flexible, maybe even closer to genuine understanding.
It helps us see the gaps we need to fill.
Precisely. It deepens our whole understanding of what artificial intelligence is and what it could be.
So as we finish this deep dive, maybe the question to leave you, the listener, with is this. We've seen the incredible power of AI learning from data mastering games, understanding speech. But we've also seen its limits, the brittleness, the lack of grounding.
So what does it truly mean for a machine to understand something? Is pattern recognition enough? Or will the next big breakthroughs require incorporating something more, maybe akin to innate knowledge or a deeper capacity for reasoning about the world?
What role might intuition or context play in building truly intelligent machines? Something to think about.